Hello friends, thanks for subscribing to my channel and commenting on my videos. A few people reached out to me for the data structure and algorithm videos. If I can make some preliminary kind of video for that. Um, Sometimes designing a system requires you to know how the data beneath your system is organized and structured. Interviewers turn and pose questions related to data structure and algorithms. So while they don't ask you to code while system designing interview, but they expect knowledge about the data structure and algorithm. So this video's purpose is to just review those fundamentals needed for the system design. This is no way a video on data structure and algorithm complete course. You are expected to know the complexity of algorithm and familiarity with the underlying data structure used. So we'll go at least superficially with those data structure and sorting algorithms needed for the system design interview. That's it. Thank you. Okay, let's start. So the first data structure is array. Array, we already know that whenever we have to store several items and homogeneous items are there, probably array is the best choice. So array is a static data structure. We need to have size estimation before we define the array. And it stores the similar item, of course, homogeneous. And insert and delete operations are order of n operations. Why order of n? That if you have to insert, then you have to move all the items to make the space for the item you're inserting. Or in the same way, when you are deleting the item, then also you have to left shift all the item to fill that gap, by deletion of that item. And fast access is provided by array. It's order of one. That's the advantage of array. If we know in C data structure, it's actually takes the base address and it's the direct, it can very quickly access to that location. That's why access is fast in arrays. Okay, moving on. Okay, so next, the very basic type of data structure in the linked list is a single linked list. Single linked list, as we know, it has the head pointer, and through the head pointer we can traverse the whole list. And the termination of the list is determined by the null pointer at the end. So you keep on moving, and in the when you hit the null pointer, it means you are at the end of the list. So it's a dynamic data structure. You can add and delete nodes based upon your need. Insert operation is order of n at the end of the list. Again, because when you are adding the item, you have to traverse the whole list till you find the null pointer, and then you can attach the node at the end. So that's why you have to traverse all the n items. So at the insert operation is order of n at the end, and insert operation is order of one at the start of the linked list, because it's very easy to tag one item at the head. So basically you create the node, and then that node's next pointer is pointed to the head, and you make that node as a head of the linked list. So basically there are three operations, but in general it's just order of one. Yeah, so linked list contains one pointer per node. Use cases for linked lists are wherever you have the ordered, you want to maintain the order of the operations or order of the list. That is one of the use case, or where you have the frequent addition or deletion. Let's, for example, the implementation of chat room in some applications. So people would be coming and leaving the chat room. So you might want to implement it as a single linked list. Likewise, we have the double linked list. Double linked list have two pointers, the next pointer and the previous pointer. So you can not only the forward movement, you can come back to the previous nodes also. So in double linked list, we move, we maintain the head and the tail. So start of the linked list and end of the linked list. So it is very useful in implementing DQ kind of data structures. Uh, so insert at each end is order of one here, because of course you have the head pointer, and you can add, and likewise you can add at the tail also. Um, Access to each item is still order of n in the double linked list, because you have to traverse the list to access that particular item. So in general, it is average cases order of n. Um, Another use case is when you implement the LRU or MRU caching solution. Um, you want to maintain the recency of that item. If it is accessed right now, you want to move that item to the front of the list. So whenever you have to pluck the item from the list and then move it to the head, so that it shows the most recent item. So that is a very good a place where double linked list can be used. Trees. So trees are very important data structures. They are not like linked list exactly, but the implementation is same in the sense that every node has the value and the next pointer, and likewise every tree can have two nodes. So in the binary tree, it can have two nodes, left and right, and access is order of log n in average case if it is ordered in binary search tree. Why it is like that? Because you have to go either left or right, and we are assuming that in binary search tree, all the left node are less than the root value, and all the right nodes are more than the root nodes value. So in general, you are dividing your search space into half. So whenever you have that kind of structure, it has the mathematical proof is that the maximum height you can go is the log n. So if you have to search an item, you can maximum go through the height of the tree. So that's why access is order of log n in average case. Otherwise, in worst case, it is order of n. Worst case would be like if you have all the items sorted, then one after another, root node, and then right node, then right node, and right node. So that could be kind of a linked list, or maybe it could be left aligned structure also. Root node, left node. So it becomes a linked list actually in that case. So that's the worst case, and in that case. Access would be order of n, because you have to traverse the whole linked list. Insert delete operation is also order of log n, because you have to reach to particular element to delete that item, or maybe if you want to insert that item, then also you have to reach to a particular, and that maximum height could be order of again log n. So that's why it is insert and delete operations are also log n. So access, insert, and delete, all three operations are order of log n if it is ordered tree, and it is balanced tree. So balanced in the sense that it is not that skewed, totally skewed structure where it becomes a linked list. Where binary search tree, there are a lot of uses, mostly like if you have to do the in order traversal. So you print the left node, and then root node, and the right node. So essentially you come up with a sorted list of elements. So binary search tree, if we do the in order traversal, we'll get a sorted array of the elements. Yeah, so BST is useful in searching, and that's one of the advantage of binary search tree. and complexity is again order of log n. Hash table. Hash table is very useful data structure from the system design point of view, because in distributed systems, we have a lot of items and we want to store them on a particular node or particular server. So in that case, we want to have that item represented by a key, some certain key, and then we see that where that key is stored. And if we find that key, we find the corresponding value to corresponding to that key. So if we see that a lot of requests are coming here, the first request, let's say it's username Alex and Aman, and we apply a hash function to these keys, and let's say they are falling back onto the first index of an array. So Alex and Aman value would be stored on this first bucket. We call it a bucket. And likewise, so this yellow portions represent the bucket, or we can say that sequential array, they represent 0th index, 1th index, and so on. So if we have n index, so we have n buckets here. So if we do index using the same function, if they fall on the same index, we store them like a linked list. That is called chaining solution. So and another term we use, that if the same key, if the different keys have the same fall onto the same key on the hash table, then it is a collision also. So again, bucket is received by, if you apply the hash function on the key, and then we look within bucket to search for a value, that yellow portion I was showing in the graph, and collisions when multiple keys maps to the same bucket. So in hash table, insert, search, and delete operation all are order of 1. So it's a very fast data structure, provided we have a very good hash function and that collisions are not happening. But if we have bad hash function, then it might happen that all the keys collide onto the same bucket. So in that case, every operation would be order of n, because same bucket would represent the linked list, because all the items would be falling onto that index, and that and then we'll adding the linked list, because as was we have the chaining solution if we have the multiple values corresponding to the same key. So that is the worst case if the collisions happen. So where the hash table used, hash table is used very aggressively for all the solution where we want the fast lookup, and it's order of 1. Graph. So graph is a very important data structure as well. Whenever you think of multiple nodes or multiple values, think of a social graph like LinkedIn or Facebook. So there are a lot of people, and they are connected with some kind of, in case of Facebook, it's a friendship relationship. In case of LinkedIn, those are called connections. So we have nodes and edges, or the vertices and edges. And so not only this, we in the networking world, all the networks are represented by the graph. And road networks also could be one example, where the cities and they are connected through the roads or highways. That could also be a very well represented as a graph. Google Map and all those places where a graph data structure is used. So to traverse a graph data structure, there are roughly 2 techniques: breadth first search and the depth first search. So breadth first search, we use internally queue, first in, first out mechanism is needed in breadth first search, and depth first search is a LIFO structure, last in, first out. So in that case, we can use explicitly as stack data structure, or we can use recursion. So recursively calling the function would use the function stack itself. So so the thing is, we can use external data structure as stack, or we can use a recursion. So complexity of visiting a graph, the access time is order of V plus E. So V is number of vertices and E is number of edges. So idea is if we have to reach certain item or access certain item, you have to, in the average case, you would be visiting all the vertices and all the edges. So that's why the complexity is order of V plus E. Okay, so coming back to the searching problem, how we search certain items in a set of list. Linear search is, as the name says, we go the linear in the one direction, forward direction or the backward direction. So we initialize an array or linked list and start at the beginning and keep on moving until you find what you are looking for. So it's pretty straightforward. And if we have n items, so it means you have to visit all the items in the list. So complexity is order of n in linear search. So binary search is very important in the sense and used very frequently because it's very optimal searching solution. Why? Because you have the array or you have the list of items and you sort them, and then you find the mid value of the that array, and then if you see that item you're searching for is more or less, and then you every time you half the search space. So for example, here if you are looking for number 69, so we have 6 elements, and so the first thing we'll find the number 20, which is exactly at the mid value, and then if the but we are looking for 69, so we'll search the right half. So left half is completely eliminated, and then in the right half we see the number 31 again. So again 69 is more than number 31, so we'll again half the search space, and ultimately we'll find the number 69. So binary search is again complexity is log n. Why? Again, the reason is same, because we are halving the search space each time. So here is the again algorithm, how it works: sort the array, check the middle value, divide the array into the 2 sub-arrays. If value you are looking is bigger than the mid value, move to the second half, otherwise first half. And we have to repeat the process in subsequent halves, like I was showing in the previous slide. And complexity is order of log n, again, because such spaces are half each time. So for searching, I said we should have the list should be sorted before you do the binary search. So there are a lot of choices for sorting algorithm. So I'm starting with a frequently used algorithm here. Quick sort is one of them. So quick sort works on the mechanism where we found where we find one element which works as a pivot, and then we do the partitioning and find the elements less than this pivot and more than the pivot in the first iteration, and keep on doing the same thing in the left and the right sub half. Um, um, so based upon this, so it's quicksort is divide and conquer algorithm, and it's very effective. It's in place algorithm. You don't need any extra space, and it is fast. Complexity is order of n log n in the average case, um, but it may hit order of n square if the pivot not chosen very efficiently or correctly. Another example, another good algorithm is merge sort. We need extra space in case of merge sort. Um, we call it external sort also in some sense, because you have to do, you need extra space or extra array for that. Um, it is stable sort. It means if we have the two items in the original list and they are identical, and if the first item is before the second item, so we'll preserve that order. So it might not happen that their values are equal, so they can the second items can come before first. So that's property. That property is called the stable, and merge sort provides the stableness property. And merge sort also scales very well to the large list of data. Again, merge sort is also quick, divide and conquer like quick sort. Insertion sort is also one of the algorithm, but it's not very effective like merge sort or quick sort, because there's very one peculiar use case where either it is already sort, or the list is very small. Then in that case, insertion sort is used, and it gives the order of n in best case, but in the worst case, it is order of n square. So, and then the previous two algorithm, merge and quick sort, they both are order of n log n. Bubble sort is not very good algorithm for sorting, but again, it's a simple algorithm, probably not to be used in the professional products or algorithm, or very important. Document search. So searching is ubiquitous phenomena, and used everywhere, whether it's a web search like Google, Bing, or mail search, or maybe we are searching in the some strings in the data center log search. So there are various tools to search the words in the documents like Elasticsearch. But I'm going to give high level idea that how search works in general. So wherever the searching comes, uh, we create a mapping between the word and the documents, or the document IDs. So let's say we have set of documents, maybe novels or something, and we create suppose there's a word, and we make a mapping of particular word to all the documents where that word is appearing. So for example, here, if we have a document, let's say document ID is 1234, and it has the phrase like winner never quits and quitter never wins. So we search for this word winner or the quitter, and let's say a lot of documents. Here I've taken one document 1234, but assume that these words appear in a set of documents. So what we do that we create an inverted index. Why it is called inverted? Because normally when we think of document, so we talk about the forward index, that this document contains all these words. So instead of document to words, what we do, we create an inverted index where word is mapped to all the documents. So here, if you see the example, a word is winner, and not only the document. So in this, we are creating this tuple kind of a thing where we have the pair of these two values, the document ID, and 125 is the document ID, and one is the index where it appears. Likewise, in the document 525, it is appearing at the third index. So not only this, we create a lot of tuples for each word, and then we rank all the document based upon maybe if we have the multiple um, uh, occurrences of a single word in one document, maybe it is a lot more relevant than any other document. So there could be a lot of ranking criterias, and it's very complex topic, but the idea is same, that we store this tuple corresponding to each word, and that's how the search works in general. And suppose if there's the whole search string, a long search string instead of a single word, then in that case, probably what we do, we create a linked list of all these document IDs and corresponding to each word, and probably we might want to merge all those linked lists and see what document ID comes in each linked list, and probably we might want to uh, deduce the common document IDs from that. So anyway, the idea is to maintain that list corresponding to each word, and then find the intersection of all those lists to find out okay, the words are common to each document. So inverted index is the a kind of we can say data structure. It is used in the document search. Another one important item is the message queues. It is widely used in the system designing problem. What message queues is actually, it's a kind of queue, as the name suggests. And idea is to decouple the system which is generating the data and from the system which is consuming the data. So in other terms, we call it the producer and the consumers. And so sometimes what happens that there are systems where the data is generated much more with the much more pace than the consumers can consume. So idea is to decouple these producer and consumers. And if for some reason the processing of data is backed up, consumers are backed up because of a lot of data they have to do. So they, instead of rejecting all the requests, we maintain that into the queue, and whenever the consumer gets the time or bandwidth to process the data items, we process at that time. So it's kind of a buffer. One example of the simple queuing service is Amazon Simple SQS, or another example comes into mind is the RabbitMQ. So entire OpenStack is based on RabbitMQ messaging queue. Again, we decouple all the services from, like producer services from the consumer services. Kafka is another one, but Kafka and other systems, I would say they are more of the real-time processing of the data. And PubSub systems, they are kind of messaging queue, but they are a little different because they are used in the lot, and there could be a lot of consumer corresponding to one so the topics and other things comes up, but the idea is same, that messages queue or message queues are used where we need a kind of buffer between the two systems. Yeah, so that's it. I just have gone through all the data structures and sorting algorithm and the main components used in the um, um, system designs. I'm sure there are a lot of other things, there are a lot of concepts, but I just wanted to give the high level idea what we should be aware of while appearing in the system design interview, and interviewer expects all these things, that we know all about this, at least high level idea about this. We don't have to code, but we should know about all this.